Hello. So in this video, we're going to be computing the horizontal asymptotes, or if there are any, of this given function. So remember, the whole sort of idea of horizontal asymptotes is that they are this n-term behavior. There are these values, y values, that eventually the function is sort of trending toward, right? And in pre-calculus, we talked about horizontal asymptotes to an extent. We came up with some rules that work sort of nicely with these sort of specific forms, these ideas of polynomial divided by a polynomial. But it was very wish-washy, right? It was sort of a nice intuitive understanding, but we didn't have the rigor we needed. So the expectation is that in this class, right, in calculus, we now have the rigor so you can prove what these things are and we can deal with more forms. So for this problem, right, when we want to look at horizontal asymptotes, what we're really wanting to know is the limit as x goes to infinity of this thing, which for the sake of maybe like general ease at the moment, I'm going to call this thing f of x, right, which this is a perfectly fine thing to do in your own work, right? Like you may be given an expression and you can sort of denote it as a function. You can say, okay, I'm going to take this expression, I'm going to call it f of x for the sake of writing some stuff succinctly. So I'm going to write this as limit as x goes to infinity of f of x. So I want to know this, and I want to know the limit as x goes to infinity, negative infinity of f of x. So I want to know the positive infinity part and the negative infinity part. And I don't know how visible that is. Let me maybe rewrite this real quick for you. Again, worth doing in your own work when you're doing this kind of thing to make sure that you can go back and understand what's happening when you try to read your own work. So these are the two things that we need. Now, again, in pre-calculus, we had this weird sort of rule about powers and stuff, but that doesn't really work in terms of non-polynomials. In this case, we have a polynomial, but in general, we don't necessarily have polynomials. And more importantly, again, it's not rigorous. So if I want to actually compute the limit, I need to be able to actually sort of show how I get the answer, right? So I'm going to start with the first one, the limit as x goes to positive infinity, but the steps overall work for both of them. So let me start maybe by showing, in fact, let me do it over here. I'm going to show sort of what would be a sensible thing to do, but would be a sort of very bad thing to try in terms of it'll lead you astray or get you to some nonsense. So I'm going to show sort of a bad approach over here, but a very intuitively natural one to try. So take limit as x goes to positive infinity of f of x, right, which is this x cubed minus 3x squared plus 2x plus 1 all over 3x to the fourth minus 2x plus 1. Okay, so a lot of the times, if you don't know what you are supposed to do, right, you're not sure about sort of what steps to take to do a limit, a very natural thing to try is to try plugging in. So that's what I'm going to do here and sort of show why this is going to go very poorly. Okay, so again, I want to emphasize that this is bad, but I want to show you why it's bad, because this is a very normal thing for students to try, and I want to show you sort of how to tell that things have gone wrong if you tried to do this. Okay, so if I try plugging in infinity, already what I'm going to write as a mathematician makes me die inside because this is kind of crazy nonsense. So you could do something like infinity cubed minus 3 times infinity squared plus 2 times infinity plus 1 over 3 times infinity to the fourth minus 2 times infinity. I'm hoping none of my fellow mathematician people in the department ever see this video for this one part, because I would catch no end of grief for having written infinity in an equation like this. So already, let me notate this here. This is already nonsense. Infinity is not a number to compute with. Meaning that we do write infinity sometimes, right? We might write that the limit of f of x equals infinity, or that x approaches infinity. But this is actually a shorthand for a concept. It is not a value that we are going to, okay? Which means that trying to plug in infinity like it's a number in an equation, that is just totally off the rails. Even from a concept standpoint, this thing does not work. This does not represent a concept. You're trying to treat it as a number, and as a number, this thing makes no sense, right? I might as well be writing bibbly bobbly boo as I go, right? Because this is not math anymore. So already this is sort of nonsense. But wait, it gets worse. So like, if I ignore that fact, which already has sort of run this off the rails, I have to sort of reconcile what I mean by infinity to a power, right? So if I think of infinity times infinity times infinity, I get something really big times another thing really big that's still really big times another thing really big. I guess that's still really big. Like I could say maybe this thing is some sort of infinity. Infinity cubed, I guess, is still infinite, right? Which again, this is sort of nonsense because you can't compute. But then I'm trying to do another thing over here where I'm doing this minus 3 times infinity cubed, or squared. Infinity times infinity is really big. Multiplying by some number is still infinity. So I'm going to get something else infinite plus something else infinite plus 1, which is really doing nothing. Then I get something else infinite, then minus something else infinite, then plus 1. So even if I ignore the fact that like computing with infinity is no longer math and I'm writing gobbledygook, here I've also run off the rails, because here if I look at something infinitely big minus something infinitely big, what does that mean, right? You might think like infinity minus infinity is 0, but that would be if it were a number. That would be if it's 3 minus 3. Right? Then it might be 0. But infinity is not a number, it's a concept. So you take something that is growing bigger and bigger and bigger and subtract some other thing that's growing bigger and bigger and bigger. Well, which one is bigger? That doesn't really work, right? So trying to do this infinity minus infinity thing, it just doesn't work. And in fact, this is what we would call an indeterminate form. So infinity minus infinity is an unknown, it's undefined. So no matter sort of what you want to claim that equals, you're wrong, because it doesn't have a value. So already this is also worthless, because this infinity minus infinity thing is going to make it nonsense. And I'll even go one more step with you. Even if somehow this were all like infinity plus infinity plus infinity plus 1, you could say like they're all positive, they're all going the same way, it's still infinitely large. You would still end up with something infinitely large divided by something infinitely large, and that is also indeterminate. And so that is also not useful, okay? So all of this to say that although it is a perfectly natural and in most cases good plan to try to plug in a number when you're doing the limit to see what happens, sort of with that info of like, even if it doesn't work, how it doesn't work tells me stuff, right? That's a good sort of mantra for limits overall. But when it comes to limits as x goes to infinity, that is just not a good way to go. It's line after line of nonsense for different reasons. So you've gone so far off the beaten path and so far off the rails that you're not doing math anymore, okay? So all of this is sort of not a good plan. But a very, like I keep saying this, but it's a very natural and a good instinct, which is why I want to show that like it's not bad that you might try it initially, but as soon as you see something like this, as soon as you start writing infinity as if it were a number and trying to compute stuff, you should immediately think like, oh God, I have gone off the rails. I am in like the deep, dark land of doom here, and I need to run away. Okay, so what do we do? If we can't do that, what do we do? So instead, I'm going to go back to this f of x and sort of notice that, like, had I done this, which I shouldn't, right? But had I done this, my fundamental problem is that I have all these infinities showing up everywhere, right? So what I want to do is be clever in a way that gets rid of these infinities in some way, gets sort of a handle on this thing so that I don't have to worry about the fact that there are infinities, minus infinities, to powers, to like all of this crazy nonsense. So the way I'm going to do that is I'm going to take my original function, this original piece here, and I'm going to multiply by 1 cleverly, which is a sentence students tend to dread when they, it's one of those things that's like, how do you come up with the clever, right? So we're gonna cover that. So the first step, maybe 1a, but again, it's going to be the same as the steps for 2, is multiply by 1 cleverly. And this is something that was talked about in some of the other concept videos and stuff, potentially, assuming you've seen those. But what we mean by multiply by 1 is really what I want to do is multiply by something over itself, and I want to choose that something cleverly. I want to choose something that gets sort of a handle on this problem. And so the thing that I'm going to sort of pull the rabbit out of the hat here is the thing I'm going to multiply by is, in this case, 1 over x cubed divided by 1 over x cubed. Now it's a thing over itself. So this thing is 1 everywhere where it's defined. It's worth a mention here, right, that it's not defined at 0, because then I have 1 over 0, which is undefined, divided by 1 over 0. But I'm looking at sort of the limit as x goes to infinity, right? This whole thing, I'm doing the x going to positive infinity, so I'm thinking of x as being some very large number. So the fact that this isn't quite right at 0 doesn't really bother me because I don't care about small x values. I'm only looking at n-term behavior, really big x values. Now, where did I get this? I got this by looking at the degree of the top polynomial and the degree of the bottom polynomial in this case. And so I want to look at sort of the x value I could divide by so that I get rid of all of the sort of x's in one of those lines. This is one of those things that's sort of hard to describe in words and easier to show. So what I did was I took the degree of the top polynomial, the degree of the bottom polynomial, and I took the smaller of those. So the top one is degree 3, the bottom one is degree 4. The smaller of those two, degree 3, that's how I got 1 over x to the 3, right? So that's where that 3 came from. Now, a good question is why? So let's see what happens when I multiply this, right? So I have, in fact, let me write this out. So I have x cubed minus 3x squared plus 2x plus 1 over 3x to the 4th minus 2x plus 1. And what I'm doing is I'm multiplying the top and bottom by 1 over x cubed. Okay, so what I'm going to write in a second is going to look really messy, but there's a method to the madness. Bear with me a little bit longer, you'll see the magic, okay? So this means that if I take, I'm going to distribute all of this, okay? So I have x cubed divided by x cubed, that's 1, minus 3, x squared over x cubed, that's minus 3 over x, right? So that's canceling I have an x squared in the top, x cubed in the bottom, so I cancel 2 of them to get an x in the bottom minus 3 in the top. So this is, sorry, plus 2x over x cubed, which is 2 over x squared, and 1 times 1 over x cubed is 1 over x cubed, divided by, and now I have 3x to the 4th divided by x cubed, so 3 of the x powers cancel, and I'm going to get 3x 1 over x cubed times negative 2 over x, so I'm going to get minus 2. 1 of those cancels, so I'm going to get an x squared at the bottom. And 1 is still 1 over x cubed. Okay. Whew. So a perfectly fair question is, good God, why? Right? Because this thing is definitely not simpler looking. But it turns out that this thing is actually a lot easier to deal with now when I'm looking at x going to infinity. So if I think about what happens when I take the limit as x goes to infinity here, I mean, let's think about it. Sort of, I'll write it out sort of formally in a second, but let's think it through. As I take x going to infinity, 1 stays 1. Easy enough. Negative 3 divided by something getting infinitely large. Well, if I'm dividing by something getting infinitely large and this thing is nice and finite, that's going to 0, right? Then I have 2 divided by something getting infinitely large. That's 0 again. I have 1 divided by something getting infinitely large. That's 0 again. So this whole top is 1 plus 0 plus 0 plus 0. It's just going to 1, right? The bottom, I'm going to get something infinitely large here. But then here, this thing is going to 0, and this thing is going to 0. So what that tells me is that this piece, the top is going to 1, the bottom is going to something infinitely large, because these are both going to 0, so I just have 3 times something going infinitely large. It's still infinitely large. So overall, this thing is going to 1 over something infinitely large, which is 0. Okay, so let me write out what we just said sort of rigorously, but this is the idea, is I've set it up in a way that now when I try to compute stuff, it'll actually work out the same way. So I guess I'm going to leave that up. I'll write it over here. So if I take the limit, in fact, let me change colors. That one's getting a little tired. So if I take the limit as x goes to infinity of f of x, that equals the limit as x goes to infinity of this same thing that I had right here, right? So this is the 1 minus 3 over x plus 2 over x squared plus 1 over x cubed over 3x minus 2 over x squared plus 1 over x cubed. Okay. And what I was sort of arguing is that as x goes to infinity, these fraction pieces, 3 over x, 2 over x squared, 1 over x cubed, this 1 over x cubed, this 2 over x squared, all of those go to 0, right? Because you have a finite number divided by something infinitely large. So this thing is going to, so let me write this in a different color because I want to write this so that you see what I'm saying, even though you wouldn't write this when you're writing out your work. So this is sort of a parenthetical, meaning like this is I'm writing this as an explanation, not as something you would include in your own work. This is going to something that looks like 1 minus 0 plus 0 plus 0 over, and this is why you wouldn't write this, because I'm treating it like a number, but remember this is just for explanation's sake. This is not something I'm claiming is mathematical. It's looking like this kind of thing, where I have 1 minus 0 plus 0 plus 0, so I have just 1 on the top. And then down here, I have something getting infinitely large, plus and minus 0, which is doing nothing. And so overall, this thing looks like 1 divided by something infinitely large, meaning that this actual limit, so I'm writing the actual line now that you would write, this actual limit equals 0, because it is something finite on the top dividing by something getting infinitely large in the bottom, which goes to 0, okay? So again, this is, I want to recap all of the stuff that I just did for x going to infinity here. So I have this original thing. I want to know about horizontal asymptotes. Horizontal asymptotes are n-term behavior. They happen when x is infinitely large, positive and negative. So I want to check both of those things. In order to do that, sort of a natural thing to try is to plug in and see, but as we saw over here, right, that's all kinds of bad because treating infinity like an actual number and trying to compute with it, right, we can think of it intuitively as this concept of getting bigger and bigger and bigger, and in some cases sort of writing it out as a concept to myself, right, as a justification, a thought process isn't terrible, but actually trying to do something numerically with it, oh man, that is all kinds of bad. You don't want to go there, right? So trying to plug it in this case is just a disaster on every level. Instead, we want to do this trick of multiplying by 1 cleverly. So in particular, we're taking the top degree, right, the degree of the top polynomial, the degree of the bottom polynomial, and we're taking the smaller of those two. So in this case, I had a 3rd degree and a 4th degree, so I took a 3rd degree, an x to the 3rd term, and I multiplied everything on the top and bottom by 1 over that x to the 3rd. The reason I did that is because really what I want to do is turn the leading coefficient or the leading power of x in one of them as, I want to turn that into x to the 0, meaning I want to make it just a number for one of those two pieces, either the top or bottom. And it's going to be whichever one is the smaller one, right? So the top one was originally the smaller degree, so the top one is now the one that has a leading term that is just 1, as opposed to x to some power, right? And the reason I do that is because now when I take the limit as x goes to infinity, this thing stays finite, because it's 1 plus or minus a bunch of stuff going to 0, because the x in the bottom is crushing down all of those numbers. And the bottom is now free to do whatever it does. In this case, it goes to infinity, right? It goes to something infinitely large here and plus or minus a 0. So I have something finite divided by something getting infinitely large, which gives me that 0. Okay, so this is the technical way, the sort of very rigorous type of way of finding the horizontal asymptote. For the part 2, meaning like if I do the negative infinity, again, as a note, this is actually really important to do in many cases because it turns out that functions can have different horizontal asymptotes on the positive side than they do on the negative side. So you do want to compute them both. That being said, in this particular example, it would be exactly the same process because I didn't really care whether it was infinitely positive or negative at any point here, right? Really what I was trying to do is set up these, by dividing by an x cubed term, I was trying to set these things up to go to 0. So whether I'm dividing by very large positive or very large negatives doesn't matter. The important thing is that it's very large. So here, part 2 is exactly the same work and process, only I'd have a negative in front of the infinity there. So I'm not gonna bother writing it out here because it's exactly line for line the same process. Okay. All right. So that is that. Horizontal asymptotes when we're looking at, in particular, a ratio of polynomials. Hello. So in this video, we're going to be determining what, if any, horizontal asymptotes this function has. So again, sort of a standard standard first step that I'm going to do is I'm going to take this whole expression bit and I'm just going to say, okay, I'm going to call this thing f of x, right, for the sake of writing stuff out sort of nicely and succinctly. And again, the horizontal asymptotes, right, this is where I want to know n-term behavior. So really what I want to know is the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x. Okay. Make sure you can see that. There we go. So, as sort of mentioned in another video, as well as concept stuff, the way I want to do this is by multiplying by 1 cleverly, right? So I do that by looking at my original function, and I want to know, okay, what is the degree of the top polynomial and the degree of the bottom polynomial. And I want to take the smaller of those two values, right? But the degree of the top, well, if I look at that, right, that is just 3. And the degree of the bottom, also 3. So here, the smaller is also the biggest, but it's 3. I don't have to worry that the same technique will still work. So since that's 3, I'm going to multiply the top and bottom by top and bottom by 1 over x to that power, x to the 3. Okay? So let's see what happens. So I'm going to take my f of x. So I have 12x cubed plus 7x squared minus x plus 4 divided by 3x cubed plus 12x squared plus x. And then I'm going to multiply the top and the bottom by 1 over x cubed. And what I get is going to sort of look very messy. I'm going to have a bunch of fractions, but this is actually a good thing. And in fact, sort of for the sake of succinctness, I'm going to be thinking about the limit as x goes to infinity this whole time. So this thing is going to equal the limit as x goes to infinity. So I'm going to distribute this 1 over x cubed, meaning I'm going to take each of these terms and divide them by x cubed. So here I'm going to get 12 plus 7 over x minus 1 over x cubed. 1 over x squared, excuse me. Always a good idea to double check, right? So this is 4 over x cubed. And really, these should all be different powers, right? Because I'm dividing different powers. So if I had a cube there and a cube there, that should be a good sign that, oh, something went wrong, right? Here, x cubed divided by x cubed, so that's going to be just that 3. This is going to be 12 over x and 1 over x squared. Okay. Now I can actually compute my limit, right? So if I have the limit is x going to infinity, then the 12 stays 12, 7 over x, that's finite divided by something getting infinitely large, that's going to 0, that's going to 0, that's going to 0, that's going to 0, that's going to, everything's going to 0, right? So this, I'm not going to write limit because I'm evaluating here. The 12 stays, the rest of it goes to 0. I'm going to get 12. You don't have to write the plus minus 0, but I'm going to do it just so that it's clear what's happening. And the bottom, the 3 also stays, and I get plus 0, meaning that really this is just 12 divided by 3, which is just 4. So this tells me that there is, I can write this out. So there is a horizontal asymptote of, so this is, right, horizontal asymptote, it's a horizontal line, so it's of the form y equals, and it's that value, so y equals 4. And to be clear, this is true to the right. But again, there's nothing special about negative infinity here, right? So I would do about positive infinity versus negative infinity. So if this were x going to negative infinity, I'd do the same exact steps. And here I'd be getting 0 each time, but I'd be approaching it from sort of a negative aspect in some sense, right? I'd be dividing by something negative and infinitely large, which would still get me 0, meaning I'd still end up with 12 over 3, which means I'd still get 4. So this is really, this shows that there is a horizontal asymptote of y equals 4 to the right, but the same work also shows also to the left. So in general, if all you have is looking at the limit of a polynomial over a polynomial, these things are sort of, in some sense, symmetric, meaning that if you find a horizontal asymptote to the right, it'll be the same as the one to the left. So if all you have are polynomials, this right-left thing you don't have to worry too much about. It'll be the same on both sides. But that's not true in general. There are functions where we can compute these limits, but they are not polynomials and they don't have the same right and left behavior. Okay? All right, that is it. Hello. So in this particular video, we're going to be checking for horizontal asymptotes. So we're given this expression and we want to know, okay, what horizontal asymptotes, if any, does that thing have? So as a sort of easy sort of thing to start with, I'm going to go ahead and give this thing a name. So let's call it f of x. Okay, so this is a good sort of thing to keep in mind when you're working out a problem. If the thing doesn't have a name, you can feel free to give it one and use that in your work as a sort of shorthand. So recall to find the horizontal asymptotes, we need to compute the limit as x goes to infinity of now f of x and the limit as x goes to negative infinity of f of x. Okay. Okay. So generally speaking, it is certainly possible that the limit as you go to positive infinity is different than the limit as you go to negative infinity for a function, sort of generally speaking. If all you have are polynomials, which is what we have here, right? Polynomial divided by polynomial, they're going to end up being the same. This has to do with how the symmetries of polynomials happen to work. Sort of when you think of a polynomial, think of a sketch of a polynomial. You have things that look sort of like parabolas or like W's, right? Where sort of the n-term behavior, they all go together. Or you have ones where they do sort of the same thing, but in opposite directions. So it might go up and down or down and up, like depending on which way you're sort of looking at it or what the coefficient is or degree, things like that. But the point is they sort of behave in a way that is predictable from one side to the other. So this is why it ends up being that way, but I want to stress the fact that this is a feature of polynomials. So if you have other things like e to the x, right, an exponential or log or square roots, things like this, that's not always the case. You want to be careful. Okay, nonetheless, we're going to start with just trying to do, okay, the limit as x goes, let's say, to infinity of f of x. So if we try that, right, again, we can't plug in infinity because plugging in infinity isn't really a thing. Infinity is not a number. But if we ask ourselves, okay, what happens as x gets really, 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 really big? Well, then our expression, right, we're going to get something getting negative very, very big and positive very, very big. So we're going to get some sort of weird infinity minus infinity nonsense in the top, and then the same in the bottom, right? Because we're going to get something big and positive minus something big and positive. So you're going to have some infinity minus infinity nonsense. But the thing is here that you're going to get infinities everywhere, right? And this tells me that what I need to do is that sort of nice technique where we divide by an appropriate power of x, right? So what we're going to do is we're going to look at the powers of both, And then we're going to divide the top and bottom by the sort of second biggest power, meaning like the power that is not the biggest degree, but the other degree, right? So the top is degree 4, the bottom is degree 3. So we're going to divide the top and bottom by x to the third, the smaller of the 2 degrees. So I'm going to do that by writing this. I'm going to write out the original f. So I have this minus 4x to the 4th plus 3x minus 11 over 13x cubed minus 17x plus 5. But then I'm going to multiply by, so I want to divide the top and bottom by x cubed. I'm going to do that by multiplying the top and bottom by 1 over x cubed. And then I'm going to distribute that out term by term and see what happens. So if I take this first thing, divide by x cubed, I'm going to get negative 4x, right? Because this is x to the 4th divided by x cubed, leaves just 1x left over. Then I'm going to have 3 over x squared and 11 over x cubed. And then down here, I'm going to have 13 minus 17 over x squared, right? One of the x's will cancel, plus 5 over x cubed. Okay, and now the idea is that I do that so that now when I try to plug in, right, again, I can't actually plug in, but when I think about, okay, when x gets really, really large, right, as x goes to infinity, well, I have something finite divided by something infinitely large. This goes to 0. As does this, as does this, as does this. So this tells me that this limit then behaves like negative 4x over 13 as x goes to infinity. So this is going to go to infinity, but in this case negative infinity. Okay. So what does that tell me? Well, that tells me that there's a horizontal asymptote at negative infinity. Now, if you think of an asymptote as this line that it can't cross, I mean, I guess that's kind of true. I mean, like, if there could be a line at infinity, I guess it's not going to cross that because you can't go bigger than infinity, or negative infinity in this case, right? But that's not really a helpful way of thinking about this thing. Like, what does that even really mean? Like, okay, it can't get bigger than infinitely big in the negative direction? Like, what? But if you think about horizontal asymptotes the other way, the way that we sort of explained it in our sort of concept introduction, horizontal asymptotes in general, are more of a sort of a line or a boundary that tries to pull the function toward it, right? And so normally if you have a horizontal asymptote of, say, y equals 2 or something, right? That's a nice line, and the function gets sort of pulled down and sort of stays really close to 2. But if we think about it, that's actually, it sort of makes sense what it means here when we say like the horizontal asymptote is negative infinity. What we're saying is that the function is getting pulled toward negative infinity, meaning it's not going to flatten out anywhere. So we say that there's no horizontal asymptote because there's no sort of finite line that the function gets sort of pulled into. But I'm pointing this out because I want to show that like the math is actually pretty consistent if you have this idea of an asymptote, that if you think of it as, okay, this is the value that the function is getting pulled toward, then this is telling me that the function is getting pulled toward negative infinity. It's getting infinitely large and negative as x goes bigger and bigger in the positive x direction. And so this thing is telling me that there's no horizontal asymptote in the sense of, a line that the function is sort of staying toward. But it's also telling me at the same time that it's getting sort of pulled down to this negative infinity over time. It's getting sort of more and more and more negative. Okay? So now I would do the same thing going to negative infinity. And if I do that, all that's going to happen, right, I still have the same problem of this infinite nonsense going crazy up here. I multiply by 1 over x cubed in both cases. I'd get back down to here. These would all go to 0, but now I'd have a negative infinity. and that would give me that I'm going to get negative, negative. So when I did the negative infinity here, I'd get a positive infinitely large thing divided by 13. So it would go to positive infinity. Again, telling me that there's no asymptote in the sort of finite sense. There's no line that it's sort of stabilizing around, but rather that the function is getting pulled up to positive infinity. It's getting infinitely large, more and more and more in the positive direction as x goes further and further left to the negative infinity side. Okay, so I would, again, recommend going through the negative infinity case on your own. Make sure it works out the same way, but it should be the same computation, just with a positive infinity as a result, because you'll have a negative with the x here. Okay, so that's that.